We've emphasized in this class that there is no position vector in a curved space. Vectors don't label finite displacements on the manifold. There's no natural vector space structure of the points on the manifold like there is for a flat space. But of course, a curved space is locally looking flatter and flatter, and so there ought to be some version of this construction, at least in the neighborhood of a point. That's what we're going to talk about next, and it's called the exponential map. And this construction is going to lead us to a coordinate system called Riemann normal coordinates, in which not only is the metric equal to the flat metric at a point, but its first derivative vanishes in accord with our expectations from the equivalence principle. To motivate the exponential map, let's remember how things work in a flat space, say the flat 2D plane. And we can pick some point that would normally be the origin, but I'm going to call it P. And then we could pick some other point, which is going to be the point x mu. In this case, there's only two coordinates, x and y. And we insist that we're working in Cartesian coordinates, i.e. the metric g mu nu is just delta mu nu, the Euclidean metric. And now we can imagine a vector, call it k, pointing from P to x, and this is the quote-unquote position vector. And what is k? Well, k also has the components x, y. This is how the map between vectors at the point P and points on the manifold works in a flat space. You just do it in this way. So that's the story in flat space. Let's see how close we can come to doing the same thing in a curved space, or a curved space-time. So now the cartoon is there's some curved manifold M, and at some given point P, we have the tangent space, which we draw as a little flat plane, but it's just the tangent space where vectors live. And we could still imagine making a vector k in that tangent space. But the vector k no longer points to any particular point on the manifold in the same way the position vector does. However, what we can use, given that we now have the geodesic equation, is that the point P and the vector k uniquely determine a geodesic curve, which then goes out along the manifold. And what are the equations for that? Well, the initial condition, I'm going to call it z mu, of lambda, that'll be our geodesic, and the initial condition is just z mu at lambda equals 0 is p, so let's say the coordinates x mu of the point P, and the initial derivative dz mu d lambda at lambda equals 0 is just k, and the geodesic equation is a second order differential equation. So giving the initial value and the initial derivative will indeed uniquely determine the solution. So these three equations determine the curve z mu of lambda. And we use the affinely parametrized geodesic equation. So each choice of k gives rise to a curve like this. If this is k1, we could draw another vector k2, that's a different vector in the tangent space at P. And that would similarly give rise to a different geodesic curve that goes off in a different direction, another z mu of lambda for that different choice of k mu. And so you see that every vector at the point P determines a geodesic curve. And in the position vector construction on the left, if you think about it, the position vector we drew is just moving along a geodesic curve from P to the point, which is the same thing as going unit affine parameter along that straight line geodesic. And so what we want to do to generalize that in our exponential map is to pick a special point, which is going to be the exponential map of k. So this point here is going to be exponential map at P acting on k1, and that point, call it x mu, is given by unit affine parameter. So we take our curve. I should have written, in this equation here, I should have written dz mu d lambda. We take our curve, z mu, and we evaluate it at 1, and that is x mu. Okay, so these 4 equations now determine a special point x mu. I'll call this x mu 1 because it's the one mapped by k mu 1. And then this one here is a unit affine parameter along the green curve. I'll call that exponential map at p of k2 is x mu 2, has the coordinates x mu 2, and so on. And so every vector in the tangent space will map to some point on the manifold. Now I'm drawing pictures here as if it all works quite nicely every time, but you should keep in mind that the existence theorem for solutions of ordinary differential equations only guarantees that these curves exist for some finite lapse of parameter, lambda. It could be that for some choice of k, when you try to extend the resulting curve to lambda equals 1, you actually fail and you run into a singularity before you reach lambda equals 1. And in that case, you would not be able to include those vectors k in the domain of the exponential map. However, we do expect, because a curved space should be locally flat, that there will be a sufficiently small region around the point P, and correspondingly a sufficiently small space of vectors k for which this construction always returns a point, and indeed for which it returns a unique point. If you go far enough away from a point P, you could have the situation where the geodesics actually cross. The red one and the green one start out going in different directions, but do that. And outside of this region, the exponential map would still be okay, but it would not be invertible because it's not one-to-one. And so what we do is we find a sufficiently small region, which I'll call this region N, where there exists a unique geodesic connecting any point in N with P. And that region is called the normal neighborhood. I'm not going to prove that there exists a normal neighborhood. It's sort of obvious, but it still takes some work to prove. But you can imagine that at least if you draw your region sufficiently near P, there'll be a unique geodesic connecting every point in this region to P, and we can freely talk about the points in this neighborhood as in one-to-one correspondence with vectors at the point P via the exponential map, which by definition is invertible in this neighborhood. Now, in flat space-time, this construction has a few key properties. First of all, we have to be in Cartesian coordinates, where the metric is equal to the Euclidean metric, here written delta mu nu. We also have the property that the origin of coordinates is the point P. In other words, the coordinates x mu of P are all 0. And then we have the third equation defining the position vector. Now in curved space, we won't have Cartesian coordinates, but at a point P, we can certainly still set the metric equal to what it would have if we were in flat space, in this case, eta mu bar nu bar. We discussed how this is possible when we defined the signature of a metric. This is just some linear algebra at the point P. And also we can use the freedom to just shift coordinates by constants to make sure that we also have the origin of coordinates, x mu bar, at this point P, needs to be 0. These are our new barred coordinates for the curved space. And the last equation, k mu equals x mu, well, we'll just flip that around and take that as the definition of our coordinate x mu bar. It's just this vector k mu that's present in the exponential map. It's really the inverse exponential map. These coordinates are called Riemann normal coordinates. So let's understand this in the curved space. Suppose we're at this red point here, some point on the manifold. It has coordinates x1 mu in our original coordinate system, and we want to know what its Riemann normal coordinates are. Well, first we make sure that at P, we've chosen these Riemann normal coordinates so that the metric has the form eta mu bar nu bar. And then we ask if we invert the exponential map to get the vector k1 mu and express it in those coordinates where g mu bar nu bar is eta mu bar nu bar, we get 4 numbers, k mu bar 1, and those 4 numbers are the Riemann normal coordinates of our point here off in the manifold by the bottom equation x mu bar equals k mu. And you can do that for any point, like the green one will The Riemann normal coordinates of the green point will be k2 mu bar, and so on and so forth. And so even though it doesn't exactly look like a coordinate transformation here, this x mu bar really is a function of x. The vector k mu bar is determined by whatever point x you have on the manifold. And these conditions together give you a definition of a coordinate system in this normal neighborhood where you can invert the exponential map. So to summarize, the exponential map at a point P maps you from the tangent space at P, the choice of vectors, to the normal neighborhood, all the points for which you can find a unique geodesic, and is defined in this way. And the associated coordinate system is called Riemann normal coordinates. So the exponential map is the closest thing to a position vector in a curved space-time, and the Riemann normal coordinates are the closest thing to Cartesian coordinates. Now you can see, of course, that they are kind of like Cartesian coordinates because, well, the metric is taking its Minkowski form at the point P, but they're even more like Cartesian coordinates, which you can suspect from their definition, and you can see from a calculation. The next thing we're going to show is that near the point P, the metric is in Riemann normal coordinates is equal to eta mu nu plus, now if you Taylor expanded, you'd have a linear in x term with metric derivatives in front, but the metric derivatives we're going to show are 0 at P, and so actually the first correction is going to be order x bar squared. And if you recall our discussion of the equivalence principle, the absence of these order x terms, we argued, was telling you something about gravitational forces not really being physical, being coordinate effects, that gravity's effect is as a tidal force. Force differences matter. And this is finally the mathematical expression. So we're going to go ahead and do the proof now that indeed, according to the definition of Riemann normal coordinates, the components of the metric have no coordinate derivative at the point P. So that's the claim, and here's the proof. It's a little subtle, but it's quite slick compared to some other proofs you'll find which involve just writing out a bunch of equations and showing there's a solution. The first thing I'm going to do is rewrite some of these equations for the Riemann normal coordinates and the exponential map and collect them together. So in Riemann normal coordinates, the geodesics of the exponential map, the ones through P, satisfy the following equations. So first of all, what is z mu bar, the Riemann normal coordinate components of a geodesic at the starting point, lambda equals 0? Well, z of lambda equals 0 is xp in general, but in the Riemann normal coordinates, xp mu is 0. So the initial condition for a geodesic in Riemann normal coordinates at point P is that z mu bar equals 0. All right. Now, we also have a final condition that z mu bar of lambda equals 1 needs to equal x mu, the coordinates of the point we're talking about. But then in Riemann normal coordinates, x mu, now called x mu bar, is k mu. So we can write z mu bar of lambda equals 1 is k mu bar, but k mu bar itself, by the equation that started all this off, is equal to the tangent vector dz d lambda at lambda equals 0. So dz mu bar d lambda at lambda equals 0. So that'll kind of collect all these equations together so we don't have to keep referring to them. And now we can proceed with the proof. And the trick is to consider a new function where instead of lambda, we write it as the product of two parameters, rho and sigma, and we define a two-parameter family of points, z hat, just to distinguish it from z, still mu bar, Riemann normal coordinates, but now it's going to depend on both rho and sigma, and it's going to be defined as the Riemann normal coordinate curve z mu of, well, where it said lambda before, we now do rho times sigma. Now, why is this interesting? Well, this curve is an affinely parameterized geodesic in either rho for each sigma or sigma for each rho. It's symmetric. We're going to say in sigma for each rho. Now, it's clearly a geodesic because it's the same curve. The only question, it's constructed from the geodesic curve, z mu bar. The only question is whether sigma should be considered an affine parameter. Well, you see, this is just replacing the parameter lambda with sigma times some constant. So this is like lambda goes to a constant times lambda, and indeed that preserves the affine parameter. Let's write out the conditions of this geodesic. So what's its initial condition? So this z hat mu, viewed as a function of sigma at sigma equals 0, well, we just plug sigma equals 0 here, but that's just the same as z mu bar at lambda equals 0, which is 0. And this should have said bar. Now let's work out the initial derivative. So now we'll have d z hat mu bar d sigma, but since this is a function of rho and sigma, I should really write partial to clarify that rho is fixed. And now I can use the chain rule on this equation to calculate partial sigma as dz mu bar without a hat, d lambda d sigma, which is just rho. And I'm most interested in evaluating all this at sigma equals 0. And so by the chain rule, this gets evaluated at lambda equals 0. But what is dz mu d lambda at lambda equals 0? Well, it's just k mu bar. And so we in fact have that this term is rho k mu bar. And finally, let's look at the final condition. What is z hat mu bar at sigma equals 1, the affine parameter where we stop for the exponential map? Well, now we just go back to the definition. At sigma equals 1, we just get z mu bar of rho. But this is actually pretty cool because we've actually constructed a new geodesic, z hat, that is the exponential map geodesic for a rescaled tangent vector rho times k mu bar, where the parameter is being called sigma, but it's still just a parameterized geodesic of the exponential map. And so in Riemann normal coordinates, we must have that the final value is equal to the initial derivative. Here it's called lambda, but here it's called sigma. It doesn't matter. It has to be that the final value is equal to the initial derivative. And so by the right-hand sides of these equations, these two things have to be equal. And what does that tell us? Well, look what happens. The hat is gone. We now have z mu bar of rho. The original geodesic curve with the parameter called rho is now explicitly equal to rho k mu bar. This is the solution to the geodesic equation in Riemann normal coordinates. And it's just a straight line through the origin. This k mu is a fixed tangent vector, and this rho is just a parameter, and it tells you that the Riemann normal coordinate components of your geodesic just move off in a straight line. So that's kind of a neat point that is surprisingly tricky to show, but conceptually very appealing. And now we just have a calculation left. We can use this to show that indeed the Christoffel symbols, in fact the whole metric component derivative of the metric vanishes at the point P. So let's see how that goes. We have the solution to the geodesic equation, and in particular we can take the first derivative, dz bar mu d rho is k mu bar, not just at P, where it was by definition of the exponential map, but everywhere in the normal neighborhood in these special coordinates of the normal neighborhood. And similarly, the second derivative, d2 z mu d rho squared, well, that's just 0. And we can use these conditions in the more general form of the affinely parametrized geodesic equation, that capital D by d rho dz mu d rho is equal to 0. And we can expand these out in terms of the Christoffel symbols to get d2 z mu d rho squared plus Christoffel mu alpha beta dz alpha d rho dz beta d rho. And now let's express this in the Riemann normal coordinates. So I can put a bar on the indices. This will hold in any coordinate system, including the Riemann normal coordinates. But now I can use these special properties in red here. This term is just 0. And this one is just k alpha bar. And this one is just k beta bar. And so I've concluded that gamma mu bar alpha bar beta bar k alpha bar k beta bar equals 0. Now it's tempting to conclude that because k is supposed to be arbitrary that the gammas vanish, but actually the gammas here are evaluated at the point along the geodesic curve we are considering. And that point actually depends on k, because the geodesic curve has the solution z mu equals rho k mu bar. So I'm evaluating this Christoffel symbol at x mu bar equals rho k mu bar. And so it's not independent of k. The point I'm evaluating at depends on k. But if I do rho equals 0, which is x mu bar equals 0, i.e. the point P, the special point we're constructing these coordinates about, then I have the equation gamma mu bar alpha bar beta bar. Well, I'm always evaluating at the same x bar mu equals 0, which is just the point P, independent of what was chosen for k. And so now I can conclude that indeed, because k can be anything and the Christoffel symbol is symmetric in the lower two indices, it must be that for this to be true for all those k's, that the Christoffel symbol itself vanishes at the point P. We're almost there. We don't have that the metric components vanish, but it's just a hop, skip, and a jump. We can use metric compatibility. Remember that del rho of g mu nu is always equal to 0. That's how we defined this covariant derivative. So in particular, we can do that in the Riemann normal coordinates, and we can expand out the covariant derivative as partial derivatives plus terms involving gamma and g. And I'm not going to write the indices because I want to do this in Riemann normal coordinates, barring all the coordinates. And I want to do it at the point P. And in that case, I have Christoffel symbols in Riemann normal coordinates at the point P, which I just showed are vanishing. And so finally, we conclude that del rho bar g mu bar nu bar at a point P equals 0. All of the coordinate derivatives of the metric in Riemann normal coordinates vanish at the point P. And so indeed, by the Taylor series, we have the claim made at the beginning of the video that g mu bar nu bar, there exist coordinates, and we've constructed one example, the Riemann normal coordinates, where it's equal to eta plus not some order x term, but some order x bar squared term. And this expresses the equivalence principle as formulated by Einstein.